My name is Angel and I'm here to teach you the disk method. But before that, let me ask you something. Are you familiar with this? That's great! It's a disk. Don't you know that disk is used to play videos and music before? That's true. Now, we have a multiple application that we can use as a music and we can watch for a video. So, let's continue to our lesson.
In this video, we're going to do our first example of the disk method. And because it's our first example, I'll try to go a little bit slowly and explain every piece in detail. So here we have a function of two vertical lines in the x-axis, and those all trap some area, which is right here. And then, what we're going to do is we are going to imagine rotating this area around the x-axis. And when we do that, what shape would we get? Well, we would get something that looks like this. And the question is, what is the volume of this solid that's formed by rotating this around the x-axis? And it turns out that there's a quite nice formula for this for the volume of that solid, and this is called the disk method. The formula is in the integral a to b of pi r of x squared dx. This is the disk method formula for when you are rotating around the x-axis. So this is for rotating around the x-axis, which you are doing in this example. It also works if you are rotating around anything parallel to the x-axis. So any horizontal line, but for now, let's focus on this. And there's a few pieces here to talk about. So these problems are all very similar, so I like to break them down in steps. And the first steps that you should always do when doing a solid revolution problem is to sketch the problem out. And since this is our first example, I already have drawn a sketch for us, so that part's done for us. We have a sketch of function and these vertical lines that are trapping. That area part 2 we're going to skip in this video. But this is decided a method, and what I mean by this is eventually we're going to have the disk method, the washer method, and the shell method. So eventually, we're going to have to decide which of these three methods is appropriate for our particular problem. But in this case, I'm telling you, we are going to use the disk method. So this decision is made for us. Okay, so again, this is our first example, so I'm keeping it easy. So step 3 is to find a and b. So if you notice in our formula, there's these bounds of integration, so we have to figure out what those are. And in the disk method, those bounds of integration are the leftmost and rightmost point of the area that is trapped. So in this case, that's also very easy. It's pretty much given to us the leftmost point of the area is just x equals 1 because that's the vertical line that's trapping it, and the rightmost is x equals 5. So these were pretty much also given to us. And just to be clear, we have a equal 1, the lower bound is the leftmost point of the area, and b equals 5, that's the upper bound, is the rightmost x value of the area. Okay, and now we come to maybe the main step you might want to say, which is finding r of x. So before we can even find r of x, we have to talk about what is r of x. And the idea here is what we're going to take this solid and we're going to pick some x value. And then we're going to imagine slaking this solid at the x value. So when we do that, what do we get? We get a circle and maybe the x isn't quite aligned with that. So let me draw that in here a little bit more clearly. So we pick this x value and we slice this solid, and notice that this slice of this solid is actually, it's a filled-in disk because we're slicing a solid there. So what is r of x? So it is the function that tells us the radius of the circle. Okay, so in the other words, for this fixed x, value of r of x will tell us the radius of this particular circle. Alright, but if we go back to our 2D picture, which is all we'll ever really need actually. And we fix that same x value, we can draw a line from the x-axis of rotation up the edge of the area. And I hope what you can see is that this distance here is r of x. It is the radius of the circle that is formed right if we took this line and we rotated it around the x-axis. We would get exactly this circle that's down here. The distance from the x-axis of rotation to the edge of the circle, that is the radius. Okay, and this r of x clearly depends on x because if we had picked this x value, the radius would be smaller. If we pick something out here, the radius would be larger, so that the radius function really depends on which x value we pick. Okay, so we know what r of x is, but how do we actually find a formula for r of x? Well, it turns out that in this case, it's pretty easy because this point lands on the function. And remember, f of x gives us the height of the function, so given this x value of f of x is the height of that point. But that height is exactly this distance from the x-axis up to the point, or in the other words, that height is exactly the r of x we're looking for. So altogether, what we find out is that in this case, r of x is just equal to f of x, which is the example is 1/3 x, which in this example is 1/3 x. Okay, because that distance from the x-axis out to the function, that's the radius of this circle down here, but that also happens to be the height of the functions. So they're the same. I hope that's clear. And now our fifth and final step is just plug in. Right, step 3 and 4 found all the missing pieces in this formula. So now, just plug into the formula, and that formula will give us the integral, will give us the volume of this solid that we're looking for. Okay, so that let's plug in here and do the integral from a which is 1 to b, which is 5 of pi times r of x squared. And in this case, r of x is just 1/3 x, and we have to square that dx. Okay, so just for total clarity, this part here is r of x according to this line, and that is just the piece of the formula. Alright, so really the problem is pretty much over. We've done of all the setup, all of the hard part, and now all we need to do is solve this integral. That part should be easy at this point. So let's go through it. But if you're comfortable with this setup, you know you could go through this on your own, or you can stick around for the last few minutes of the video where we actually saw the sound full, but I just want you to be aware that the problem is pretty much over. We've done all the hard work already. Okay, so with that in mind, let's go ahead and actually solve this. So this is equal to the integral from 1 to 5 of pi, and now we squared 1. This is equal to the integral from 1 to 5 of pi, and now if we square 1/3, we get 1/9 square x, and we get x squared, and we can pull out that constant pi times 1/9 is pi over 9. Integral from 1 to 5 of x squared dx, and now we can take the antiderivative using the antiderivative power rule, so we add 1 to the exponent, so that's x cubed divided by the new exponent, and then we have to evaluate that between 1 and 5. And so let's go ahead and make some more spaces for ourselves. So this pi over 9 times, we plug in 5 and we get 5 cubed over 3 minus, then we plug in 1 over 1 cubed over 3. And so this is pi over 9 times 125 over 3 minus 1 over 3, and the whole thing simplifies to 124 pi over 27. Okay, and this is our final answer. This is the volume of the solid we had at the beginning of the video. That is the volume of the solid of the revolution we are looking for. Alright, so I hope this helps. In the future videos will more advance this method example.
Bye, hope you enjoyed the video.